Hello, this is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and in this video I'm going to go over the solutions for the winter 2019 E&EL 343 exam number 2. And so, like exam number 1, we start off with some short answer problems, and so I'm just going to verbally go over these. So question 1A, explain why an inductor is not a very good battery substitute. And basically the reason for this is because an inductor needs a constant current flow in order to store energy in its magnetic field. And so you can't disconnect it from a circuit and move it around and then reconnect it and harvest that energy. The current has to be flowing basically all the time. And because of that, it's not a very good battery substitute because it can't just sort of sit there by itself and store its energy like a capacitor can potentially. So that's basically what I was looking for. A few people said, you know, it requires a change in current to generate a voltage, and that's true, but that by itself doesn't necessarily make it a bad battery substitute. It's really the fact that you need to have constant current flow in order to store energy. The second question was, how do we take the projection of one signal onto another? You basically multiply the two signals together and integrate. So, you know, a few of you will have seen me writing this on your exam. And that's kind of what I was trying to convey. So you basically take, you know, your first signal, multiply it by the second signal, and integrate. That's how you take a projection. And you get a large value if the two signals are similar, and you get a smaller value if the two signals are not similar. And, you know, a few people said, you know, you take the projection by taking the Laplace transform. That's kind of true. I mean, I guess you're taking the projection of the signal onto the Laplace transform signal, if you like, e to the minus st. But I was looking for something a little more general than that, a more general answer. For question C, how does an inductor store energy? Basically, magnetic field. And if you had the words magnetic field, you got the 2 marks. And I think pretty much everybody did that. And finally, D, what's the difference between an overdamped and a critically damped response? Lots of people drew a picture, which I accepted. So an overdamped response, you know, it takes a while to go up to steady state. A critically damped response, so if this is overdamped, a critically damped, response looks like that. It's basically the fastest possible convergence to the steady state value without going into oscillations. And I accepted that. I accepted a picture. I accepted even people just saying that a critically damped system has 2 identical real roots, and an overdamped system has 2 distinct real roots. Okay, in question 2, we talk about using an inductor as a very crude, uninterruptible power supply, or UPS. And the purpose of this UPS is to supply a voltage to a device for a little while, even after the main voltage source fails. And so in this question, we're assuming that we have a 10-volt DC power source. So Vs, and Vs is equal to 10 volts. And we have a light that is modeled as a resistor, a 100 ohm resistor. And the first part of the question, part A, is to draw a schematic showing how the inductor would be connected to act as a UPS. And the correct connection is to connect the inductor in series with the resistor. And when the voltage source fails, which is described in this question as going from 10 volts right down to 0, what's going to happen is the inductor is going to generate a positive voltage in order to maintain the current flow around the loop, and that will keep the light on for a period of time. And the light, we've said in the question, remains on as long as the voltage across this resistor is 7 volts. And this was, so for part A, I was just looking for this connection. And there were a few people that hooked the inductor up in parallel. So we had this kind of configuration. However, this won't work, and I took 2 marks off for this because at steady state conditions, a inductor is a short circuit, and so if you hook the inductor up in parallel with the resistor, it shorts out the resistor and the light can't be on. So the correct answer is to have the voltage source in, or the inductor in series. Now for part B, we have, for part B, I ask you to determine the value of your inductor so that the light will remain on for 1 second after the voltage source fails and drops instantly from 10 volts to 0 volts. And that's kind of a hint because basically this is the source-free response of this circuit. So when we go from a voltage supply of 10 volts down to 0, it's basically the source-free response. And the question then asks you basically, what does the value, if we call this V out, what value of inductor is required in order to keep V out above 7 volts for 1 second? And so this is basically the source-free response of this circuit, and we solved this on the assignment. And so V out of T is equal to our initial voltage source, or our initial source voltage Vs, multiplied by e to the minus t L divided by R. And we substitute in 10 volts here, e to the minus t, oops, sorry, and t is 1 second. L is what we're solving for, R is 100, and this is equal to 7. And if we solve for this, L is equal to 280 henries. Okay, for question 3, this was the oscilloscope question, and the first part of the question was where to connect your 2 scope probes in order to measure both the current flowing into the circuit and the voltage across the output when for the step response of this circuit. And so we can indicate the location just on the diagram. Channel 1 would be, so the channel 1 positive probe would be connected up to here. The channel 1 negative probe, or the ground connection, would be connected to the ground of the circuit. Channel 2 positive would be connected to the top of the capacitor. And channel 2 negative, or the channel 2 ground, would be connected to the ground of the circuit. And then for the remainder of the question, I'm basically just looking for a description of your sort of general approach to solving this stuff. So I'm not looking for actual calculations or general, or sequences of buttons or anything like that. So for part A, how would you estimate the correct volts for division setting on the vertical axis? Basically by knowing kind of how big the step response is, and we know roughly how big the step response is going to be if we know roughly how big the input voltage is going to be. And so that's basically what I was looking for. So if people said, you know, I would estimate it based on the size of the input voltage to the circuit, you know, I accepted that. Some people went a little bit further and said, well, you know, I would double it to account for the possible overshoot due to underdamped response. That was good as well. Oh, also I should say, for this scope connection part of the question, some people just only indicated one connection, which I understood as the positive part, and that was fine. However, a few people did put, for example, the positive part of one scope probe on the left-hand side of the resistor and the negative part of the scope probe on the right-hand side of the resistor. And what that actually does is connect this part of the circuit to ground, because the negative part of the scope probe is actually connected to the ground of the oscilloscope, and that will short out the circuit. So I took marks off for that. Moving on to part B, how would you estimate the correct seconds per division setting on your horizontal axis? Basically by knowing how long the step response is going to be calculated based on your knowledge of R, L, and C. Would you use math mode? The answer is yes. So in order to determine the current flow into the circuit, we would have to have the voltage across the resistor. And so that means we have to calculate, or we would have to use math mode and get it to display the voltage of channel 1 minus channel 2. And that would give us the voltage across the resistor, exactly like we did in the lab. What trigger mode would you use? Because we're capturing a one-time event, the step response, you would have to use the single trigger mode, or snapshot trigger some people put in, which, you know, I accepted. A few people, I think maybe a small handful of people talked about how they would set up the signal generator to generate periodic pulses, to generate the step response over and over again, and then trigger the scope based on those pulses. That would work, so I accepted that. And finally, will the scope display your results in proper units, or will you need to do a conversion? Well, when we look at channel 2, the scope normally displays things in terms of voltage. So channel 2, because we're looking for the output voltage, would be fine. However, channel 1 minus channel 2 would still give the results in terms of volts, and we would like those in current, so we would have to divide by the resistor R. Again, just like we did in the lab. Okay, question 4 was the circuit analysis question, basically. So we have 2 resistors and 2 capacitors. So I've redrawn the diagram with a few more kind of intermediate things. I'm going to define the voltage between the resistors as V1, the current through capacitor 1 as IC1, and then the current around this loop as IR1. And there's a couple different ways that you can analyze this circuit, but I chose to use Kirchhoff's current law at this node. So the current going in, which I'm going to call I1 is equal to the current going through capacitor 1 plus the current going through resistor 2. And the current flowing into the circuit is just equal to the voltage difference across R1 divided by R1. So we have V in minus V1 divided by R1 is equal to the current through capacitor 1. So that's C1 times dV1 dt plus the voltage difference across R2 divided by R2, V1 minus V out divided by R2. Now, a few people correctly noted that the current flowing through this branch is also equal to the C2 multiplied by the derivative of the output voltage, right? And so this could also be C2 dV0 dt. That was totally valid. However, a few people set up their equation this way, and then they said the current through capacitor C1 was equal to C1 times the derivative of the output voltage. And that was not correct, right? Because the voltage here is obviously not the same as the voltage at that point. So I took some marks off for that. A few people also set up a current equation that said basically that the total current flowing into the circuit was equal to the current flowing through C1. They didn't account for the current also flowing through this second branch. So there were some marks off for that as well. A few people also said that, they recognized that this was an intermediate voltage, but they said that V1 was equal to R2 over R1 plus R2 V in minus V out. And you can't use the voltage divider equation, or if you want to use the voltage divider equation, you have to account for the other things connected at these nodes as well. You can't just sort of choose one path and neglect these capacitors. So the folks that did this also lost a few marks. And that was basically a lot of the mistakes were on this sort of initial setup of the problem. And then once it was set up, it was basically just sort of moving through the algebra. And, a few people made algebra mistakes, but actually not very many. Most people, if you did lose marks on this question, it was because of how you set up your initial problem. So with the way I've set up this problem, obviously V1 is something we want to get rid of. When we're deriving a transfer function, we want an equation only in terms of V out and V in. And so what my next step was to sort of group the V1 terms on the left-hand side of the equation. R2 V1 equal to V naught over R2 plus V in over R1. And V1 is equal to the output voltage plus the voltage drop across the resistor, which is just IR2 times R2. Whoops. And the current flowing through resistor 2 is the same as the current flowing through the capacitor, C2. And so it's equal to C2 dV naught dt. And so V1 is equal to V naught plus C dV naught dt. And I'm going to take this and substitute it in here and there. So we have C1 d dt times V naught plus, oops, that's a 2, C2 dV naught dt. And so we get a double derivative here, plus 1 over R1 plus 1 over R2 V naught plus C2 dV naught over dt. Again, equal to V naught over R2 plus V in over R1. And, we can sort of expand this out and group some terms. We take the Laplace transform of this, and I'll spare you sort of all that algebra. I'll just show the end result. HS is equal to V naught S over V in S, 1 over R1 times R2 C1 C2 S squared plus C1 plus 1 over R1 plus 1 over R2, R2 C2S plus 1 over R1. And there's a lot of different ways that you can express this transfer function. Lots of people who had exactly the right answer didn't put it in this form, and that's fine. This is just one of the forms that you could have had. And so obviously you can multiply by R1 and you can do a lot of simplification here, but this is, basically the correct answer is some mathematical equivalent of this final expression. Oops. Okay, this is the solution for problem 5. Problem 5 was taking this input signal and determining the output voltage from this circuit. Now, step 1 is basically to express this input signal in terms of the unit step function. So this is equal to 2 times the unit step function minus a unit step function that's delayed by t, that causes the first step down, minus another unit step function that's delayed by 2t, that causes the second step down. When we take the Laplace transform of these three terms, we have 2 over s for the first step function, minus 1 over s, and then e to the minus ts, that's the minus t delay, and then e to the minus 2ts, that's the delay of the second step function. The transfer function of this circuit is something that we solved on the assignment. This transfer function is equal to RCS over RCS plus 1. A few people made the mistake here. Some people gave the transfer function for this circuit, which is h of s is equal to 1 over RCS plus 1, but that's not the proper transfer function for the circuit in the question. So the next step is to take our input signal and multiply it by a transfer function. The nice thing about this is that the s's here cancel that s, and so there's actually really no need to do partial fraction expansion. So the first term is just 2 times s plus 1 over rc if we divide or multiply the top and bottom by 1 over rc. The second is a delayed version, the third is a delayed version. And then when we take the inverse Laplace transform, we get an exponentially decaying term multiplied by 2, a second exponentially decaying term delayed by t, and a third one delayed by 2t. A few people delayed the unit step but forgot to delay the exponential function as well. The minus t and the minus 2t has to also be contained up there. And finally, for problem 6. Problem 6 is basically a situation where we have a series RLC circuit where the capacitor is charged up, and when the switch is closed, we essentially have the source-free response of that circuit across a light interface, a second light interface circuit, and basically when the voltage across the capacitor, and here's the picture. So when we close this switch, we initiate the source-free response of this series RLC circuit. We have the voltage across the capacitor, just like we did in the lecture notes. And basically when this voltage is on, when the voltage is positive, the light turns on, and when the voltage is negative, the light turns off. And the first part of the question says we want to basically have an oscillation that will turn this light on and off. So the pattern, the light should be on for 100 milliseconds and then off for 100 milliseconds. And so if this is the voltage across the capacitor, decaying with time, actually, it's easier to show here. So we want it to be on for 100 milliseconds. So this duration is 100 milliseconds. And then we want it to be off for 100 milliseconds. So this should be 100 milliseconds as well. And so the period of our oscillation then is actually 200 milliseconds. And since we're assuming that this is an underdamped system, we don't have to determine the transfer function or anything like that. We can basically just go to our expression for damping frequency. And we know that in an underdamped system, the damping frequency, WD squared, is equal to omega naught squared minus alpha squared. A few people had a plus here, so that was a small mistake. And then omega naught is equal to 1 over root LC. Alpha is equal to R over 2L. We have the value for resistance. We have that value for inductance, so we can plug those values in for these two terms, and only C is the unknown. Omega D is equal to 2 pi times 1 over 200 milliseconds. And I did take a mark off if people forgot the 2 pi, because it's a radial frequency or an angular frequency rather than just hertz, which would be 1 over t. And then if you go ahead and plug in all these values and you solve, you get C being equal to 398 microfarads. And then for part B, you know, I did try to be very careful with my wording on this particular exam, but I did make a mistake for part B. There was a misunderstanding. So the question was, how long before the amplitude of V naught decays to 2 volts? When I said amplitude, I was thinking about amplitude in terms of sort of the classical sense of a sinusoid, where amplitude is the peak of the sinusoid. And so what I was basically asking for, or what I wanted to ask was, you know, we have this kind of envelope that causes the, you know, the peak amplitude of the sinusoid to decay. And this envelope is given by e to the minus alpha t, right, where alpha is the Nipper frequency. And actually, I guess this would be, you know, our initial voltage of 5 volts times e to the minus alpha t. And so I was basically wondering, what I wanted to ask was, when does this envelope decay to 2 volts? And so it would be 5 e to the minus alpha t is equal to 2. We know the value for alpha, and you solve for t, right? So it was meant to be very simple. However, I know that basically everybody interpreted amplitude as the actual sort of voltage of the signal, and so people were trying to solve for when this part decayed to 2 volts, which is a much more difficult question, and it's not a question that I would consider a fair exam question. And so I just didn't mark B. I gave everybody the marks for B, and then I just essentially only marked A for this question because of that mistake.